All right, everybody, thanks for coming to the session. My name is Nick Whiting. I'm the technical director of VR, AR, XR. Basically, if there's an R in the acronym and it's involved with Epic, I probably do it. And I'm going to go through a technical post-mortem of a game that we recently released called Robo Recall. So first of all, I think it's useful to kind of give some context. How many of you guys have actually played Robo Recall? All right, that's actually the best numbers I've ever seen. So a lot of this might be kind of review for what's in the game and whatnot. But as a little bit of backstory, Robo Recall kind of started at OC2 with a demo that we did called Bullet Train. And Oculus came to us. They had these new touch controllers, which they said, hey, they're pretty cool. We should try making a game. So in about 6 weeks, with a motley team of between 3 and 8 people, we made a demo called Bullet Train, which was basically kind of Matrix fantasy action style. You had guns, you had stuff you could throw at people, you could grab rockets and throw them back at people. And then after the success of that one, Oculus came to us and said, hey, would you guys be interested in taking the concepts that you developed for Bullet Train and kind of turning it into a full-fledged game? And that was kind of how we started with Robo Recall. So in order to get everybody kind of on the same footing, even though it seems a lot of you have played it, I want to show a quick trailer of Robo Recall so you can kind of see what it's all about.
Say hello to the latest member of the Robo-Ready family. Presenting the TAL Series 9. Every bolt, every component has been meticulously designed. TAL will obey any command. It lives to serve.
Serve this.
We are now getting reports of such robot violence.
TAL features convenient transport handles,
Why did they add handles?
as well as easily replaceable parts,
Hey, I'm using that.
and is built from impact-resistant materials.
Booyah!
Trouble-free service is guaranteed by our Robo Recall program.
Ow, 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 ow. What now? Robot heaven, I see it. Unstoppable.
Making your life better, one robot at a time.
So as you can see, we were really trying to elevate cinematic storytelling and deliver a deep moral message about society and whatnot. When in reality, we just wanted to have a lot of fun and make you feel like a badass. We kind of wanted to take the same fundamental kind of arcadey style, Neo Geo style action that we kind of prototyped in Bullet Train and then see what happens if we actually had a budget and a team to do something with it. So when we were trying to go about defining what our kind of budgets were and our metrics for performance, we really had to decide what were the pillars of the game that we wanted to actually spend our performance on, because you kind of have some options. You know, you can invest in certain things at the expense of other things. So it really helped to define kind of 4 fundamental pillars of what Robo Recall was. The first one was we wanted to really keep the fast and frantic action gameplay. So we knew that we had to have a lot of objects on the screen. Everything had to be buttery smooth. And we really needed to have a lot of gameplay that was not only predefined, like pulling a trigger on a gun, but emergent, like throwing the gun when you get frustrated at somebody and getting a reaction from that. We also really wanted to kind of deal with the physicality of the robots. We wanted, since you had these touch controllers, we really wanted to say, what would it feel like to tear a robot apart? We couldn't actually send people robots to tear apart, but we wanted to spend a lot on physical animation so you got the impression and we can give the illusion that you're actually tearing something apart when you're not tearing something physical. Next up is this was actually the first game that shipped with our rewritten audio engine for Unreal, and we really wanted to kind of push the boundaries of that. A lot of people, when it comes to VR, pay a lot of attention to the graphics of it, but not a lot of people pay attention to the sound. And we've noticed that sound actually makes the environment feel real. You get a lot of spatial cues, in fact, out of the reverb in a room or the effects that are going on in the sound. It's the other half of how we perceive the spaces around us. So we wanted to really spend a lot of CPU budget on actually making a soundscape that was worthy of the game. And finally, we wanted it to feel like a live, real environment. So that basically implied we wanted to have a lot of effects that made it feel grounded in kind of a fantastical reality. Everything was a little bit more colorful. A lot of the locations were based on San Francisco, but you might notice it's a lot cleaner than real San Francisco. So we wanted shiny environments, lots of reflections, things to really make it feel like you're in a real space. So if you've ever worked with artists as an engineer, you know that they always adhere strictly to the budgets that you give them. They never try to do more than they're actually given. So we had a futile attempt of defining what we thought was a budget for Robo Recall. So these were kind of based on a combination of what we were shooting for, which was the Oculus recommended spec of a 2.7 gigahertz machine with a NVIDIA 970 GPU or an AMD 290 GPU. And based on what we had learned from Bullet Train in terms of performance. So for the environments, since that's kind of the centerpiece, we wanted to have these large open environments that you could explore. We decided to dedicate about 900 draw calls and 1.8 million polygons to it. And then putting the robots and the other interactables in the world, we decided to give a budget of an additional 300 draw calls and about 0.4 million polygons to fill that out. And interestingly enough, we also had to consider what our actor budget is. And in Unreal, actors are things in the world. So they get updated every frame. They are a collection of components. We wanted to have a lot of those things to make the city feel alive, a lot of things that you could actually interact with. But we specified that we could have about 1,600 of those at any given time in the scene. But we wanted to keep less than 250 of those actually active and doing things and alive around the player. So we tried to make our gameplay focus around the objects that are immediately interactable around the player. So before I move on and talk about why we made some of the decisions and how we did it, I think it's useful at a more kind of fundamental level to understand a little bit of the threading model that we have in Unreal Engine 4, because it adds a little bit of context to the stats. So before anybody says anything, this is a greatly simplified view of how we do it. I know a lot of render programmers at HQ are probably shaking their heads at me right now for simplifying their beautiful rendering pipeline. But if you break it down, there's really kind of three main components that we have to look to optimize. The first one is the game thread. The second one is the render thread, and that also interacts with the GPU, obviously, because we actually have to draw the stuff to the screen. And then for us, we also were able to take advantage of the new Unreal Audio Engine's threading model down there. So that was something that we had to consider for performance and the trade-offs there. So when it comes down to it, the green here represents CPU stuff, and the orange represents the GPU stuff. And when we boil it down to what we actually have to hit, it kind of comes down to this really simple magical formula. And it's the CPU time, all the green stuff has to be a little bit less than 10 milliseconds in order to make frame rate. Plus the GPU time, which is another about 10 milliseconds, has to be less than 2 frames. And if we hit those numbers, then we should make frame rate, and it should be a comfortable experience for everybody. So in order to test how we're doing, there's kind of two different ways to go about doing it. The first one is built into the engine. If you bring up the console and type stat unit, it'll show you how much game thread time you're taking, how much render thread time taking, how much your total GPU time is taking. And that's good to get a quick check. But that's basically not entirely accurate, because the Oculus compositor is running in the background. It requires a little bit of CPU time and a little bit of GPU time. So this is what we think we're doing, but there's like a couple gotchas that I'll go over. The other way to do this, which is more accurate, is use the Oculus Perf HUD, which is an external tool. It's run by Oculus, and it tells us what Oculus thinks we're using. And truth be told, it doesn't really matter what the engine thinks it's using. Oculus controls the presentation to the headset, so what they say is actually what we have to target. So going back to the three kind of groupings, I'm going to break these down each a little bit one by one so you can understand what sort of optimizations you can make in order to improve time depending on when you're going over budget. So the first one is what I call the game thread and friends, because the game thread basically comes down to everything that you're simulating in the world. So any of your blueprint visual scripting, any of your gameplay code, your input handling, physics, networking, and most especially the actor ticking, the thing that makes these objects come alive in the world, are all governed by the game thread. So we can't control the order in which things tick, and we can't tick the actors in parallel, unfortunately, but we can control them a little bit by the tick groups that you see up there. We kind of grossly divide them into 3 different groups. There's a little more fine granularity, but the ones that we care about are the pre-physics tick group, the during physics tick group, and the post-physics tick group. So the one thing we can split out is the animation graphs. So all the animation blueprint work that we did in Robo Recall could be evaluated in parallel, and that's what those little white boxes are representing. Those are little worker thread processes. So there's a set chunk of work that has to happen every frame. As we move objects around the scene, we have to process collision, we have to process interactions and stuff like that. So there's this chunk of work that's always fixed. What we can do is take some of those actors that are ticking, and if those actors aren't going to affect the outcome of those physics collisions, or if they can tolerate a frame of latency, we can tell the engine to tick those objects within the during physics tick group so that we get some degree of parallelism out there. And that lets us hide some of the actor ticking time. So for Robo Recall, which was codenamed Odin, which is why you see Odin up there in all of these, there's a lot of classes that were doing a lot of work every frame that didn't necessarily affect the ticking or the position of objects. So things like the AI manager that was trying to figure out what the AI should do and issuing commands to it. The speech manager, which is the narrator that's telling you got combo points. The wave spawner, which is deciding when and where to spawn enemies. The physical audio component, which was doing all the calculations as you rip the robot apart. The straining and cracking that you hear is all governed by those audio components. In addition to kind of our game mode and gameplay, things that were keeping score and spawning stuff for you. All those didn't rely on the outcomes of any physics calculations, so we could push those into the during physics tick group. And that actually ended up saving us quite a bit of time. So aside from that, the biggest offenders that we saw, number one thing is if you have too many ticking actors in the scene, that really bloats your game thread time. As I said, we tried to keep it under about 250 active actors within your radius at any given time. But when you're going through and debugging, if your game thread time is too high, the first thing to do is, are there any actors that are ticking that shouldn't necessarily be ticking? Even though ticking is cheap, if you're not doing much in it, it does add up if you start to have thousands and thousands of actors on the screen. The next are timelines. And timelines in Unreal Engine lets you do cool things like add curves. So if you wanted to make a blinking light, you can make a curve in the editor, and then the light would get brighter and darker as per the timeline. On their own, that's not very dangerous. You can make a light, add a timeline component, and it's blinking. Where it becomes dangerous is if you add that light to the scene, and then a level designer goes and copies it hundreds and hundreds of times, and all of a sudden you have hundreds and hundreds of timelines ticking in your scene. So that's another thing to go check. One thing that doesn't necessarily affect your kind of steady state frame time, but affects hitching, is spawning objects. It's a very heavyweight operation in the game. So whenever we got hitches, we would always take a look, are we spawning a bunch of things in the middle of the frame? Are we creating too many robots in the same frame? There's things you can do to amortize it. Fortunately, VR apps are running at 90 frames a second. So if you space things out over a couple of frames, perceptually, people aren't going to notice that they weren't instantaneously done. The other two affect steady state are the kind of physics and collision. If you have too many things in your scene that are trying to do collision and overlap, it gets very expensive because each one of those has to be processed and has to go down to the physics engine. It costs a lot of time. And then animation, which you just have to optimize by simplifying your animation blueprints. The next thread that we kind of dove into is the render thread. And the render thread handles all the stuff that happened on the game thread, turning those into things that are actually being drawn. So in VR, because latency is important, the first thing we do in the render thread is we do a late update. We read the latest position from the HMD and then use that as our final view position. And that makes the experience feel a little bit more comfortable because we're able to hide the latency of the game thread because of it. So in general, we do the update from there, and then we traverse the scene to see what we have to draw, and then we generate draw calls based on that. There's a little bit of parallelism in here because we have what's called RHI, which is our render hardware interface. Creates a bunch of jobs that go through and actually create the draw calls that we send to the GPU. Those kind of go parallel in the depth pre-pass and the base pass and the translucency pass, the velocity pass, and then they combine back together to issue the draw calls to the GPU. There's a couple things that are kind of easily tweakable when you're going through and trying to optimize your program, but the biggest one that affects it is the total number of scene draw calls. When the render thread goes over, that's the first thing we check. We see, are we blowing that up? Usually the case is we are. And if so, we try to use things like instancing or mesh combining to improve it. We also, for Bullet Train and Robo Recall, implemented instanced stereo rendering, which gave us kind of free wins across the board. I'll talk about that a little bit more in a few minutes. The next thing that's costly is occlusion and scene complexity. So we have to decide what we're going to render, especially in a big kind of semi-open world game like Robo Recall. We have to call out the objects that the user can't see, so we make the most efficient use of the GPU time. But the more complex the scene, the more time that takes. So I'll go through a couple ways that we can improve that a little bit later, both on the programmatic side and on the artistic side. And the last thing is kind of a gotcha that I like to mention. If you have any stalls on GPU tasks or compute tasks, that can also affect the render thread, because if the CPU is waiting for the results of that job, you can delay it actually sending more work to the GPU and starve it. Next up is the audio engine. Like I said, Robo Recall was the first Epic game to start leveraging the audio engine. And it was actually really, really powerful, because for the first time we actually had control over the mixer, and we had control over how many worker threads that we could actually use to try to parallelize out some of that work. So the main audio thread is kind of similar to the render thread in that it's taking all the information from the game thread and turning that into audio things. So if you play a sound, if you play a mix, if you want to do occlusion of audio, if something goes behind a wall, all that's handled in the audio thread. It then spawns off these little source workers and decoding threads, and these decompress the audio effects. So if you play a gunshot that's compressed, it does the job of decompressing it. It does sample rate conversion. It also does things like HRTF, so head-related transfer function that helps you really kind of localize the sounds. All those are done in worker threads. And then we finally pass it off to the audio hardware thread, which is different per platform. It's kind of like kicking it off to the GPU, except it's on the CPU generally. So one thing of note is that you can control the number of these worker threads that are on there. So if you had 32 sources and you had 4 worker threads, each one would process 8 channels of sound. You can go as wide as you want. That's all configurable in the game's configuration files. But one of the things that we ran into is we just decided to go wide first off, and on lower end machines, we actually started starving the rendering thread because we were using too many worker threads for the audio engine. So it's something to be aware of, and I'll talk about it a little bit more when I get to scalability. So with all that said, I'm going to do a quick review of how to profile an Unreal Engine so you can see where the problems are, and then you can go and attack them. The first one that I mentioned was stat unit, and this is kind of really useful for answering the question, am I CPU bound or am I GPU bound? It kind of looks like you see up there where you get a frame time, which is your total frame time, and then the game time, which is the game thread time, the draw time, which is the render thread time, and the total GPU time. As I said, this is kind of what the engine thinks it's using, and it's not necessarily entirely accurate from the perspective of the Oculus compositor. So you have to be a little bit careful. We use this for kind of gross testing, like are we completely blowing the budget or are we still good? One thing that comes up a lot, and I like to reiterate in these talks, is that a lot of times people will say, I added a mesh to the scene and all of a sudden my frame rate tanked from 90 to 45. And a lot of people think that it's the result of that one mesh, and it's really not. The Oculus compositor blocks us kind of like you would with a VSync. If you don't make frame rate, it throttles you for a frame so that you have enough time to finish that out and present it the next time that the headset actually does VSync. So it's not the fact that that one mesh dropped you all the way, those 45 frames a second. It's kind of the straw that broke the camel's back. You were really on the cusp, and then that one thing kind of drove you over the edge, and it tanked completely. And when that happens, these numbers are very hard to interpret. So if you're at 45 frames a second, don't necessarily trust stat unit. If you do find yourself in that situation, though, there's a handy little trick that we use to basically take the performance characteristics of the HMD, except render it without worrying about the Oculus compositor blocking you. So if you launch the game with emulate stereo on the command line, it'll kick it into stereoscopic mode. You can set the resolution to 2160 by 1200, which is the native resolution of the Oculus device. And then you can set the screen percentage up to 140, which accounts for the oversampling that we have to do in order to reach a pixel density of 1 on the device. The nice thing about this is you can actually see what your game and draw thread times are unencumbered by the simulated VSync that the Oculus compositor does. So if you're doing profiling and trying to narrow down things, this is a great way to do it without actually having to worry about the compositor messing up your stats. Another useful trick, which seems really, really stupid, but is to pause the game. If you pause the game and you're trying to debug the render thread, you don't have to worry about the game thread and stuff kind of getting in your way and changing the situation. So a lot of times when we're profiling things, we pause the game and then we use the different show commands which turn on and off features like static meshes or particles or lighting. And we kind of get an upper bound of how much savings we can get. So if we turn off particles and see that we can save 3 milliseconds in that scene, that's probably a good target for optimization. So we actually leverage pause, as stupid as that seems, quite a bit. The show flags, if you type show, you'll see an autocomplete list of a bunch of show flags. It's also in the documentations. We use that to kind of target artist-driven optimization. So particles are expensive in this scene. There's too many animating skeletal meshes in the scene. If you turn those on and off, you kind of get an upper bounds, and that helps you target your performance improvements. A couple other useful things are stat anim and stat physics. This shows you things like how long your cloth or destruction you're taking. And stat anim, which was very important to us because we were leveraging the physical animation system, it tells you how long your animations are actually taking to evaluate. Again, you can kind of get an upper bound and see if it's worth investing in optimizing those particular portions of your content. Stat scene rendering is pretty useful. That lets you see your draw calls and your other render thread info. You can kind of see if you're way blowing your budget here. That's the first thing we did when QA reported a hitch. We had them bring up stat scene rendering, see how many draw calls and triangles were in the scene, and see if we just had completely blown the budget. Another useful one is stat dump hitches. This lets you set a T hitch threshold, which is a threshold in number of milliseconds. And if the game thread or render thread takes longer than that time, it'll actually dump out a stats profile that you can look at later. So this is really useful if you set it to over 11 milliseconds. Anytime you drop a frame, it'll dump out a stat log file, and you can go in and see what was causing that. So if you have hitches from spawning, that's a great way to find them. For more kind of in-depth profiles, what we would have QA do is run through the game, and when they noticed the frame rate started tanking, we would have them type stat start file, which starts logging performance data, and then stat stop file, which stops logging it. And then you can bring it up in the Unreal Engine Performance Analyzer, which looks kind of familiar to anybody who's used Visual Studio or VTune or something like that. It's just kind of basically a hierarchical performance analyzer that you can use to drill down and figure out where the problem is. The nice thing about this is it works for both native code and blueprint code. So if your artists or designers have done something nasty in blueprints, you can find it in here. So as I mentioned before, you really need to be careful when you're interpreting the data when you're not hitting frame rate because of that throttling. When Oculus pauses us, the way that our Unreal Engine stat system works, that time that it's holding us appears in different areas. So if you're looking at a profile and you see the occlusion time is suddenly ballooned to 11 milliseconds, it's not actually the occlusion time ballooning to 11 milliseconds. That's just where the stat got aggregated. So if you're not making frame rate, go to the emulate stereo mode that I mentioned before, and that's usually a more useful way to actually get accurate performance data. So kind of in summary, if your game thread's too high, the kind of checklist for the top 4 things we do is reduce the number of ticking actors that you have in the scene, reduce the number of colliding objects because that's a very expensive operation, try to hide work during physics groups so you get better parallelization on there, and then finally, as a last resort, check the number of components that you have in the scene. There's a pretty amusing case in Robo Recall that I'll get to in the game Post-Mortem, where we realized how many components we were actually moving in a scene, and we ended up saving about 6 milliseconds. If the render thread's too high, the first thing we attack are draw calls. Draw calls, draw calls, draw calls. That's almost always the quickest thing and the easiest thing to save. You can improve those via instancing or some other tips that I'll tell you in a minute. You can merge meshes and use instancing. We had our developers make a few tools that if you selected a group of assets that use the same mesh, it would automatically create a new blueprint that created instances of those meshes, and that takes the n number of objects that you have and turns them all into one draw call. One thing that's useful, especially on mobile actually, is if you stream or hide levels or actors that you know you're not doing as you're going through your level, that saves the number of things that we have to consider for scene occlusion. That helps cut down your render thread time. And finally, as a last resort, the delete key is always a fun one. Take somebody's hard work, delete it, and all of a sudden your frame rate is faster. Many tears though. So next I'm going to talk about some of the rendering thread and GPU optimizations and how you can kind of improve those. The first thing we did was instant stereo rendering. And as I said, draw call is kind of the most important arbiter of how slow your render thread time is. So with Bullet Train, we implemented what's called instant stereo rendering, which is where we take one draw call and then use a user clipping plane on the GPU to actually draw the same thing twice using the instancing hardware, and then let the shaders take the view-dependent info through a packed buffer that we send it. On Bullet Train, we did this for just the base pass and the early Z pass, and that saved about 1/4 of a millisecond for free, which is great because we didn't have to do any work on the content side in order to get that. For Bullet Train, we added support for instant stereo rendering in the translucency pass and the velocity pass, and that saved about 0.2 to 0.5 milliseconds in Robo Recall, which was actually about a 50% savings for the translucency pass. So it was nearly a perfect 50% optimization, which we were pretty psyched about. And that's automatically on in the engine if you use instant stereo rendering. You can also save time by using pre-computed visibility volumes. And what this is you place one of those rectangular volumes in the level, and it computes what objects are visible from within there. So you're basically trading a little bit of increased memory usage for not having to do as much runtime computation when you're there. We use this a little bit. It's very content dependent. Some people have great savings with it. Some people don't see any savings at all. It's worth giving a shot. It increases your lighting build times in the editor, but it could potentially save you quite a bit on the runtime cost. The next one is mesh combining and instancing in order to save draw calls. So if your artists are going through and placing a bunch of kind of rocks or detritus on the streets and it's the same mesh, you can go through and make those all into one instance static mesh, and that takes n number of objects and turns it into one draw call. So we had a lot of that for the trash that was on the street or columns or decorative architectural elements. If there's a group of them that will always be in the same kind of view, you can turn those all into instances and save some draw calls. The next thing that we added, it was in order to avoid having to use a bunch of dynamic lights. So we tried to use almost exclusively static lighting in VR just because of the performance considerations. But one of the problems with that is you basically can only have one lighting scenario for your levels. We had a small team and we couldn't generate a lot of physical geometry in the time that we had. So we decided we wanted to try to get as much use out of possible from the same geometry. So we had daytime and nighttime scenarios for each one of the maps. So this is what it looks like in the daytime with static lighting. But we also added the ability to relight the map and then bring in static lighting to change it into a nighttime scenario. And this let us get a little bit more mileage out of the content without actually having to spend any more cost for dynamic lighting. Next up is forward rendering. So we were fortunate enough to have Oculus implement forward rendering for us in Unreal Engine as kind of a test case for some of their demos. The Dream Deck demo with the dinosaur and whatnot used the work done by Pete Demerol at Oculus. They used clustered forward rendering. And based on the success and learnings that they had, we decided to integrate it into our own pipeline. So while they kind of wholesale replaced our renderer, we decided to actually add it in as a pass in our normal rendering. So if you look at the overall Unreal rendering pipeline, we kind of go from an early Z prepass, which goes through and then kind of renders the depth data for everything. We do our normal deferred rendering pass, and then we added in this clustered forward pass, which is kind of a traditional forward rendering method, but it has some of the benefits of being able to support a lot more lights than a traditional forward pass. And then we add on our post-processing. By adding that in as just part of our normal lighting pipeline, we get a lot of benefits from that. We can combine forward and deferred rendering, so if you want to render some things in a forward style, some things in a deferred style, you can do that. But it also gives us the flexibility if you want to not use the G buffers from the deferred lighting, you can get a pretty sweet memory and pixel optimization. It also lets us, if we want to, do deferred style lighting. So this let us do a little bit more complex lighting and shadowing on the clustered forward pass than we would be able to do if we just wholesale replace the renderer. And another side benefit that we got from it was that we have the ability now to do lit forward translucency, which is something that we didn't have in the engine before, but looks really nice. So for Robo Recall, what we basically did was turn off the deferred pass and turned on MSAA. MSAA was important for us because we have a very kind of clean style in Robo Recall. The robots have a lot of very clean lines. MSAA lets you really get the sharpness from that, whereas temporal anti-aliasing has a little tendency to kind of smooth things out and blur them up. It doesn't look quite as good, especially with the style that we were going for. You'll notice, though, we keep on the early Z prepass, and that kind of confuses a lot of people because people think that's for deferred rendering only. But given that kind of depth information that we get from the beginning with the clustered forward information that we have, that lets us do a bunch of the lighting tricks that we wouldn't previously be able to do. So we get a little bit of the information that we would have in a G buffer without having to actually render out the entire G buffer. So here's a kind of quick overview of the supported feature set of forward. It's clustered based, as I said. We have MSAA, which is important for the look. We have dynamic lights, capsule shadows, and shadowed movable lights. But one of the things that was essential for the visual style in Robo Recall, as I said, was the planar reflections. And these are the puddles on the street where you can see the robots running through and the reflections from it. It kind of accentuates the bombastic action. All the particle effects look really good when they're reflected in the street. So that was one of the things that we spent a lot of time optimizing and trying to get working properly in the forward rendering pass. So to get to some specific numbers about it, we noticed that if you were to compare apples to apples in the same scene in Robo Recall with the deferred renderer, it was about 12.3 milliseconds. With the forward renderer, it was about 9.56 milliseconds, and that was on an NVIDIA 970 card. But the interesting thing is everybody, when we were talking about forward rendering, thought it was going to be the savings from the getting rid of the G buffer overhead. But of those kind of just shy of 3 milliseconds that we saved, only about 0.7 milliseconds was actually from the G buffer overhead. The rest of the time was actually because the forward render is able to make much more intelligent choices about which fragment shaders it uses as it goes down the pipe. And in addition, we noticed that it's a little bit more efficient on AMD hardware than it is on NVIDIA, because we think that the AMD hardware is just a little bit friendlier towards forward rendering. So one big caveat is forward rendering is faster, but nothing comes for free. We immediately take all those savings that we got from the forward renderer and throw that at MSAA in order to increase the visual quality of the scene. So in the end, it's kind of a wash in terms of performance, but we feel that the visual clarity actually lends itself to making the style of the game a little bit better. There's also kind of an interesting side effect of that, which is we can actually scale up and down using the Oculus adaptive resolution stuff much farther in the forward renderer. So temporal anti-aliasing has a tendency to smear content, and when you accentuate that by dropping your pixel density even lower, it really exacerbates the problem. So in Robo Recall, from an artistic standpoint, we only wanted to go down to about 90% pixel density with the temporal anti-aliasing, because after that, it looks like you got Vaseline in your eyes, and it's just terrible. With the forward render, we could go down to about 70% pixel density, which let us cover a much wider range of GPU hardware. So we think there's still a case for both. We still use the deferred render in some of our digital human demos, but it does limit you to only using temporal anti-aliasing. But on the bright side, you get that access to the G buffer, which is full of rich data that you can use for screen space ambient occlusion, subsurface scattering, things that are very important for certain rendering styles. You get full access to all those features with the deferred renderer and kind of maximum versatility. So there's still a market for it. We find a lot of enterprise people still like to use the deferred renderer over the forward renderer. But a lot of people that are in the games market are switching to the forward renderer. So you get the choice between MSAA and TAA. If your MSAA hardware is particularly slow, you can still use TAA. You get a faster overall rendering pass, but you have to rely on more specialized rendering features. You don't get the access to subsurface scattering and screen space ambient occlusion. But it kind of gives you the maximum scalability range. So if you're trying to hit the widest variety of hardware possible, we recommend going with the forward renderer. Now, when you go to a forward renderer, there's some things that you kind of have to consider a little bit, especially if you turn on MSAA. When you get sub-pixel geometry, you can get what's called a moiré effect. So if you look up on here, you notice the stripe lines at the top, kind of around this area, you'll start to see wave patterns kind of emerging in there. And that's an artifact called moiré. And where this really bit us on Robo Recall, where the facades of the building have a lot of kind of, bumpy geometry on them to make them look realistic. And when you're looking down a street at them, a lot of that geometry kind of goes at a glancing angle, and suddenly you have a lot of triangles in each pixel. And when you do that, you start to get these moiré patterns emerging on it. So it looks like all your buildings have these weird wavefronts. So to combat this, the solution was thankfully very simple. We just built LODs that kind of simplified that subpixel geometry and flattened it out, and that problem goes away. No more subpixel geometry, no more moiré, no problem. But more importantly, if you look at this is a heat map of how much overdraw we're getting per pixel. So the brighter and hotter the color, the more GPU time we're spending on the scene. You'll notice that in the foreground, we're pretty good, but as you start to get at those glancing angles on buildings, it starts to get red hot. And that's because when you use MSAA and you have subpixel geometry, you kind of exponentially grow the fill cost for each one of those pixels. So what you have to do is reduce the triangle count, again, through using the same LODs. And the good news about that is you get an almost linear benefit. So in this particular scene, we reduced the triangle count by about 31%, and we got about a 27% speed up on the geometry pass, and that's almost a linear gain. It was 1.7 milliseconds on a 970, which is huge for us, and it's something that we needed to do anyway. So we highly encourage people to look and pay attention to the overdraw if you start switching to the forward renderer, because it's one of the only things you can do to optimize and get linear gains out of it. The other thing that people have to pay attention to is specular aliasing. So with our physically based render, we have to be careful about shimmering. If you have textures or specular, temporal anti-aliasing does a good job of kind of averaging those out. But if you go on to MSAA, you don't really get an anti-aliasing effect on the specular channel. So you notice a lot of like popping and fizzing, people call it. That's all solvable in the shaders, but you have to go through and make sure your artists are kind of understand what's causing it and how to reduce it. So that was the other big thing that we had to update when we went to the forward renderer. So next up, I'm going to talk a little bit about the game thread optimizations, now that we got the render thread mostly covered. So the big thing that came for Robo Recall was it was the first game to ship with blueprint nativization. So blueprints are a visual scripting language, and the majority of our game code was actually written in blueprints, not in C++. So we had a lot of blueprint code, but you pay a penalty. It runs in a virtual machine, so you have communication between the native layer and the virtual machine layer, and that causes overhead. So what we did was we made a nativizer that takes that blueprint code and translates it into C++ that we can then compile and link and run natively and not pay those penalties. So we found that it was highly content dependent. We were expecting pretty big speedups, but as much as I hate to admit it, our designers are actually pretty good about making clean blueprints that are programmatically correct. So we only found that there's about 1/4 of a millisecond speedup per frame. But where it really helped us out was when we were spawning objects. We took some things that had about a 24 milliseconds hitch when we were spawning a bunch of robots and a bunch of effects, and it smoothed those down to about 4 milliseconds. So that takes us from hitching for over 2 frames to hitching for less than 1 frame, which is a great improvement, and that helped us by not having us to go through and having to optimize each one of those spikes. We just got this kind of blanket smoothing. One thing that we did notice, though, was when we ran it through our native profilers, there was still a lot of time being spent in stupid math functions that the compiler would normally optimize. So addition, multiplication, basically every one of the math functions, we weren't getting a whole lot of optimization from. So we had to do some work to refactor those and hint to the compiler that you can actually inline those functions in our nativized code. So we redid that, and we actually found that it got about 0.2 to 0.4 milliseconds savings, which was, again, pretty huge for getting it for free. We did the Kismet math library as an example, but in your projects, if you have a lot of these kind of helper functions that are very simple that you add, and we found that people like to do that for their artists if they're making a blueprint-driven game, we urge you to go through and take a look and make sure that all your functions are inlined by looking at the math examples. So the eternal question that we always get asked is, how much of my gameplay should I write in blueprints and how much should I write in C++? And it's kind of a personal question for me because before VR, I was working on blueprints, and one of the things I really wanted to do was democratize game development. I wanted to make it so that programmers and designers could all speak the same language and work on the same project, right? If a designer has a good idea, I want him to be able to implement that and test it without needing to throw the ball over the fence for a programmer and wait for something to come back. So we really, at Epic, embrace the blueprint democratic development philosophy, but a lot of people are worried, especially engineers. They're like, they're not programmers, they're gonna do something, it's gonna tank our frame rate. We're really afraid of that. I wanted to point out, this really depends on your team. If you have designers that you're willing to mentor and teach kind of just some simple best practices about how to program, it pays off exponentially with the amount of kind of creativity that you get. We've had animators add features to our games. We've had producers add features to our games. All of a sudden, these people that have great ideas can actually act on them. And with the help of blueprint nativization, it's less of a kind of scary, you're going to tank our performance concern. You can ensure basically that you're going to get actual shippable performance out of it. So I highly encourage you to embrace it. As I said, I'd venture to guess about 80 to 90% of our gameplay code in Robo Recall was built by designers in blueprints. So I wanted to go over a few of the game-specific optimizations that we had. This was specifically where Robo Recall was wasting time. So we spent a lot of time trying to get the engine in the best shape possible, but we still had a game on top of that, and games can do dumb things. So at this point in the presentation, I want you all to imagine an adorable picture of a corgi that was maybe a little bit too tubby, trying to jump over a bar, and then think about the tragic loss because the lawyers made me take it out, because I didn't have rights to show the corgi on the screen. So lawyers are corgi-hating bastards, but I digress. Yeah, exactly. So right before Oculus Connect last year, we were about to show Robo Recall for the first time. We had a kind of nasty surprise. We were told that we were going to be able to run it on 3.2 gigahertz machines, but it turned out we actually were going to have to run it on 2.7 gigahertz machines. And we found out about this on Friday before Oculus Connect, and so we had to kind of desperately shave a little bit of time off of our game thread. So we stuck it in the profiler, and we found that nearly 5 milliseconds on these 2.7 gigahertz GPUs were taken up by our movement code alone, and that seemed absurdly high to us. So to understand what was happening, you kind of have to understand what happens when you actually move an actor. So when you call move actor, it contains a bunch of scene components. Each one of those scene components you have to call update transform. Potentially you have to do swept collision checks. It has to generate overlaps events. There's a lot of these kind of knock-on effects that happen from that. And when those scene components have scene components, the problem just grows exponentially. So when you look at the robots, the game was all about grabbing things and interacting and tearing them up. So if you look at the components that are defined on there, each one for an interaction point had one scene component to tell where on the robot was a grabbing point. They had a collision component to show you where you could grab those objects. And then we had little sprites that were animated to indicate for UI, and potentially other little hint points for our UI and grabbing system, and the sound effects from tearing those limbs apart. When you look at all the ones on a robot, you have his head, his torso, his left arms, his right arms, his left leg, his right leg. There's over 50 components on each robot that every time you moved, you had to update and generate collision events for, and that got super expensive. So we looked at the gameplay of Robo Recall. If you look at our little tubby player here, he's maybe, as far as he can reach is represented by that little semicircle. So you notice of the 7 bots that are on the screen, only one of those really needs to do all that work to update the collision. For the rest of them, it's wasted because he can never extend his arm out far enough to grab them. So what we actually did was add a component that every tick checks the distance of the robot to the player and then says, if I'm over about 2 meters, then detach all those collision components and just let them be in idle. That way, when we have to move the robot, you don't have to pay the cost to update all those components. So it goes from a bunch of expensive bots to one expensive bot and a bunch of cheap bots. And as they say on the internet, that one simple trick actually cut our game thread time in half and was essential for us to actually be able to show at OC3. So we were able to rest easy Saturday night before everything else started exploding. But we got one good night of sleep, and that's a win. The other thing that we noticed was there's a lot of frame hitching when things would happen. If you look at this GIF in particular, when you shoot the guy and he dies, we spawn a bunch of chips out from him. That's really important to kind of capture that bombastic action feel, but it's not the greatest things in terms of performance. When we put it in the profiler, you can see the orange spikes in there. Those are about 14 to 20 millisecond spikes every time you would shoot and kill a robot, and it would spawn those chips out. And that was no good for hitching and comfort of the experience. So we could spawn up to 15 of these chips. So the first thing we did, we originally were spawning about 30 to 40 of these chips. We decided to cut it down to more manageable levels. But to further optimize it, we decided to pool the chips. So instead of spawning new ones each time a robot died, we would just spawn a pool of about 20 to 30 of these chips. And each time we used it, we would just move the chip to the right position and tell it to start playing the animation. So we didn't actually have to pay the cost of creating and destroying those chips each time. That brought the hitches that we were seeing from about 14 milliseconds down to 6 milliseconds. So the graph looked more like this. The purple spikes are much, much lower, and then blueprint nativization helped chop the top off of those and make it so we weren't dropping frames. So they were still a performance hit, but we decided not to optimize them any further because we figured it was asynchronous reprojection would save us. We wouldn't have an uncomfortable experience. This was good enough to ship, basically. If we wanted to take it farther, one thing you could do is actually use instancing to create all these chips and then have one actor that's controlling all of them in the physics simulation. But that was the bang for buck of investing in that work just wasn't there for us. So another thing I wanted to talk about was the custom scalability that we made for Robo Recall. As I said, we were a really, really small team, so we didn't have a whole lot of time to fully leverage Unreal's custom scalability settings. Unreal provides a very, very powerful set of scalability where you can tweak all sorts of variables depending on the hardware detection, but since we only had a few people and a little bit of time, we didn't really have time to fully embrace and take advantage of all that. So we went with a much simplified version of it. So what we do is when we initially launch the game, we run our benchmarking tool, which gives us a CPU score and a GPU score, and that's just a number. So you could have a CPU that's a 300, and you could have a GPU that's a 200. What we did was we had our QA go through our hardware compatibility lab and see what these various hardware configurations benched at. So we could associate a 2.7 gigahertz CPU with a 200 score and a 4.2 gigahertz with a 400 score. Same thing with GPUs. And based on those, we would have our art director and our lead designer actually go through and decide kind of intelligently what trade-offs they thought would be the least visually degrading for the experience based on each one of those hardware platforms. So it was a lot of QA work, but we figured it was very, very hand-tuned. It wasn't as kind of automatic as just derezzing things. We really got our lead artist and lead designer to go through and make intelligent choices about what we scaled up and down. For Robo Recall in particular, this is kind of our matrix. So the lower spec is on the left, the higher spec is on the right. For our cutoff, we basically had 2 levels for GPU and CPU. If you had a weaker GPU, which was less than a 3.2 gigahertz machine, we turned off the planar reflections. Even though they were cool, they were really expensive because they're adding to your draw calls. We disabled the reverb and EQ effects in the audio engine, and we brought it down to 24 audio channels, so 24 simultaneous sources being played. If you had a better CPU than that, we turned back on the planar reflections, enabled the reverb, and bumped it up to 32 channels so you can get a little bit richer soundscape. On the GPU side, we turned the low-quality VFX toggle, which is just a shader toggle that our particle artists and our material artists were able to go make intelligent choices based on whether or not the benchmark set it high or low. We also turned off adaptive because we noticed on some cards and some GPUs, adaptive was actually costing us a little too much performance because of the nature of how the cards allocate texture memory. But on the high-spec machine, we let it go from 0.7 to 1.0. We also, the easiest savings of all of them was turning MSAA down to 2x on low-spec GPUs and turning it up to 4x on high-spec GPUs. In addition to all this, we also gave people the ability to override anything internally through our menu. If they wanted to make different choices than we did, you could change all these on a per user basis. So there's a few things that we wanted to get to via for Robo Recall, but actually didn't have time. So these are things that we're looking for in the future. The first one is super frustum culling. So right now, we kind of do the dumb thing where since you have 2 eyes, we cull the scene for the left eye, we cull the scene for the right eye, and then draw those. What we'd rather do is cull the scene once for the combination of both those frusta and just traverse the scene once. And when we were experimenting during Robo Recall, we tried this, and it saved us about 1 millisecond to 1.5 milliseconds on our low-end CPUs. So we think that this is going to be a pretty big gain. We're hoping to get this done in the next version or 2, but this is, we think, the kind of last low-hanging fruit on the render thread optimizations that we can do. The next one is actually thanks to the work of our friends at Oculus, specifically Remy Palandri, who's a very brilliant, gifted programmer, had implemented monoscopic far field for mobile rendering. This is available right now on the mobile renderer, and we've seen about a 25% speed up on Sun Temple, which is the content that you see here. But what this does is it takes advantage of the fact that as objects go farther and farther out, the stereo separation, the distance offset in each eye, gets smaller and smaller until eventually it's not noticeable because it becomes less than a pixel. So we can take advantage of that by rendering only the things in the near field in stereoscopic, and then we can render everything in the far distance as a monoscopic, and then composite the two together. And with that, you get about a 25% gain on mobile performance. And we think in a game like Robo Recall, where we have lots of big open worlds with lots of longer vistas, we can really take advantage of that and get optimization for basically free. The visual degradation using this technique is very, very minimal. So we have very high hopes for this on the GPU front. And then there's just one more thing. So in November, our CEO, Tim Sweeney, said, hey, wouldn't it be cool if we added modding? Because shipping games is easy. We need another thing to keep you guys busy. So we decided that we should add modding. And the reason for that is kind of threefold. The first one is that Epic has always had modding in its DNA. Tim, our founder, his first game, ZZT, was built around making an editor and extensible content as you ran through this little maze game. And up through Unreal Tournament, we really embraced the community of modders. In fact, a very large percentage of the people, including myself, started out learning to program in modding, UT specifically. So we hire a bunch of those people. It's always kind of been in our DNA. The next one is we really wanted to empower the community to build upon the framework. You know, we made certain choices in the design of the game, but we realized that not every one of our choices is necessarily the best choices. We want to give people a great foundation to build upon and then try new things. So we wanted to really get the community involved, start experimenting in VR, because nobody knows what the best practices for VR is. And if they tell you that they do, we know they're lying. So we really wanted to let people take what we built and throw the spaghetti at the wall and see if anything cool that we overlooked or thought was a bad idea actually stuck. And the last part, and probably one of the most important parts, is that making VR is really freaking hard. And we really wanted to give out as much exemplary content as we can. So we released our previous demos, Couch Nights, Showdown, and Bullet Train. We wanted to do the same thing with Robo Recall because it was the largest amount of content that we had generated specifically for VR yet. So we wanted to give that out to people. And so we put the entirety of the source code and almost all of the content, except for the specific submissions that make Robo Recall, onto our launcher. So anybody can download it, tear it apart, see how we did scalability, see how we optimized our content, and build upon that. It's really a great educational and documentation tool. There were 4 major classes that we wanted to set up that we thought people would want to mod. Weapons, everybody loves to add new weapons to their games. Maps, we thought level design would be a big thing for people. New enemies, and also player controls. So in terms of the challenges with making that, the first one was at the engine level. How do we make the engine make the mods accessible and discover that mod content? And what we did was take the asset registry, which we use for the content browser to discover all the assets in your project, and then we extended that so that at runtime, we could actually find pack files that were mod files and hook those up so the engine had a semblance of an idea what kind of content you had on your machine. At the gameplay level, we knew that the gameplay needed to know how to access the new classes. So if you wanted to override the pistol with my fancy pistol, we had to have a registry to tell it how to do it. And the registry was nothing more really than a pairing of an origin class like the normal pistol with an overridden class, which is like my fancy pistol. And then finally, in the mod editor, we knew that we needed to make it easy because we figured that mod editors were people that didn't necessarily want to start from a blank canvas and download Unreal Engine 4 and work from nothing, but they also needed something to actually begin with rather than a blank canvas. So we decided to make some easy buttons where you can click and package mods just like you package a project, and we also gave them some content. We put Kalari from Paragon, we took the hands from Twin Blast and Paragon, levels from UT, and some melee weapons from Fortnite, and gave people kind of starter packs so that we make it as easy as possible to set up a new mod. When we released it, what players actually cared about most of all were custom controls. Kind of recurring theme on Reddit is everything needs onward controls. And even in the keynote yesterday, you saw everybody loves onward controls. And we specifically shied away from that because we felt it wasn't a comfortable experience for the widest base of players, so we concentrated on the teleportation angle. But to our great joy, somebody within a week of releasing Robo Recall added onward controls and stick movements to it. MGS Studios made a great control mod, and we actually gave them an Unreal Dev grant for their efforts. And it's great because that takes the hardcore audience that's really looking for that and caters to them without us having to worry about making a potentially uncomfortable experience for the mass market. People also tweaked with the teleportation, added all sorts of custom controller support. It's great. We always get asked, hey, we have this new piece of hardware. Can Unreal Engine support it? Can Robo Recall support it? Now we can say, go make a mod, and anything can be supported. And finally, we didn't have time to finish the third sensor support for the 360 tracking that Oculus announced last year. But fortunately, within about 2 days, the community had done that for us. So we had Oculus third sensor support. And so it actually really turned out great for us. It let us take some of the rough edges and let the community kind of experiment with those and try out different things that we didn't want to risk. And with that, that's everything. Thanks, everybody, for attending. I think we're out of time for questions because I went a little long, but thanks, everybody.